Did you know that the efficiency of power plants, these massive machines literally powering our world, can start as low as, say, 26%?
Yeah, it sounds surprisingly low, doesn't it?
It really does. And yet, engineers are constantly pushing them now past 60% efficiency. How do they even pull that off? And what does that actually mean for us, for the electricity we use every day?
It's a fascinating story of constant innovation.
Well, today we're taking a deep dive into exactly that. The world of vapor and combined power cycles. We've gathered some really in-depth source material for you. Think of it as your shortcut to understanding the complex engineering behind generating electricity.
That's right. Our mission today is basically to extract the most important bits, the key takeaways, so you walk away feeling genuinely well-informed, but hopefully without your head spinning.
Exactly. No information overload.
We'll start with the fundamentals, the kind of theoretical ideal cycles. Then we'll get into the real-world challenges engineers bump up against. And then the fun part, the really clever modifications that have boosted efficiency so dramatically over the years. Things like reheat, regeneration,
Right.
powerful combined cycles, even some more exotic stuff like binary systems.
Okay, lots to cover. Get ready for some aha moments, because some of this engineering is just incredibly smart.
It really is.
All right, let's unpack this. When we talk about ideal power cycles, the ultimate theoretical benchmark, that's the Carnot cycle, right? For a vapor system, we're picturing this perfect cycle happening inside the saturation dome of something like water.
Precisely. It's the gold standard for efficiency between two temperature limits. Perfectly reversible, no losses.
And it has those 4 steps.
Yep. 4 key processes.
Right.
First, you've got reversible isothermal heating. That's in the boiler, where the fluid absorbs heat but stays at a constant temperature.
Okay, constant temp heating.
Then, isentropic expansion in a turbine. So perfectly efficient expansion producing work.
Got it.
After that, reversible isothermal condensation rejecting heat in the condenser, again at a constant temperature.
Constant temp cooling.
And finally, isentropic compression. A compressor brings the fluid back to the start, ready for the next cycle. All perfectly ideal.
So if it's so ideal, the most efficient cycle theoretically possible, why don't we just build Carnot cycle power plants? What's the catch? There's always a catch.
There is. And it's a big one, rooted in practicality, or rather impracticality. Several things make it basically impossible to build.
Okay, like what?
For one, that ideal isothermal heat transfer, the constant temperature heating and cooling. In a two-phase system like boiling water, it really limits your maximum temperature. For water, you're stuck below its critical point, around 374 degrees C.
Why is that a limit?
Because above that point, water doesn't boil in the conventional sense. It becomes a supercritical fluid. And doing heat transfer isothermally perfectly constant temperature with a single-phase fluid is, well, it's really difficult, practically speaking. So that temperature cap seriously limits your potential efficiency right off the bat.
Ah, okay, so you can't get the steam hot enough in that ideal way. What else?
The second issue is the turbine expansion. That isentropic expansion sounds great, but it causes the steam's quality, the amount of vapor versus liquid, to drop significantly.
It's wetter.
Exactly.
Yeah.
You end up with steam that has a high moisture content, maybe less than 90% vapor. Imagine tiny, high-speed liquid droplets slamming into the turbine blades.
Ouch. Like sandblasting, basically.
Pretty much. It causes severe erosion and wear. Real power plants just can't tolerate that. It would destroy the turbines.
Right. So no perfectly ideal turbine operation. What was the third thing?
The compression step.
Yeah.
Trying to isentropically compress that wet two-phase mixture back to the starting point. It's incredibly difficult to control precisely. You need a very specific mixture quality and designing a compressor to handle 2 phases efficiently.
Yeah.
It's just not practical.
Okay. So Carnot gives us the absolute theoretical ceiling, the best possible efficiency, but it hits these practical walls. Can't get hot enough easily, ruins the turbine, can't compress the wet stuff properly.
You nailed it. Ideal theory versus messy reality.
So, the first big lesson. Theoretical perfection often means practical impossibility. Engineers are always balancing efficiency dreams with what you can actually build and run reliably.
That's the game.
And that brings us to the Rankine cycle, right? This is often called the ideal cycle for actual vapor power plants because it kind of works around this Carnot problem.
Exactly. The Rankine cycle makes some smart compromises to be practical. Key differences. It superheats the steam in the boiler, getting it much hotter than just saturated vapor.
Okay, pushing past that 374 degrees C practical limit for isothermal heating.
Right, and crucially, it completely condenses the steam back to liquid in the condenser before pumping it.
So you avoid trying to compress that difficult wet mixture. You just pump liquid.
Precisely. That solves two of the biggest Carnot impracticalities right there.
So what are the 4 steps in the ideal Rankine cycle?
Okay, 4 internally reversible steps. 1. Isentropic compression in a pump. You take saturated liquid water, pump it up to the high boiler pressure,
Okay.
temperature increases only slightly.
Pumping liquid, not compressing vapor, much easier.
Much easier. 2. Constant pressure heat addition in the boiler, or steam generator. The high-pressure liquid water is heated up, boils, and then gets superheated into a very hot vapor.
So you add heat at constant pressure, not constant temperature, like Carnot.
Correct. 3. Isentropic expansion in a turbine. That superheated vapor expands, spins the turbine, produces work. The steam usually leaves as a high-quality mixture, mostly vapor, but some liquid.
But not as wet as in the Carnot case, hopefully.
Hopefully not, especially with superheating. And 4. Constant pressure heat rejection in the condenser. The steam turns back into saturated liquid, rejecting heat usually to cooling water from a river, lake, or maybe cooling towers using atmospheric air that's dry cooling, saves water.
Got it. So pump, heat, expand, condense. All fluids staying mostly in phases that are easier to handle.
And that's the core idea.
Okay, so how does this stack up? What does it mean in terms of energy out versus energy in? How do we quantify its performance?
We use thermal efficiency just like before.
Yeah.
Network out divided by heat in. Or sometimes the heat rate, especially the US BIC2 per kilowatt hour, lower heat rate is better.
Right.
Now, for a typical ideal Rankine cycle, say, steam entering the turbine at high pressure, moderate superheat, condensing at a decent vacuum, the thermal efficiency might be around maybe 26%.
Okay, 26%. That's quite a bit lower than the theoretical Carnot potential you mentioned earlier, which might be over 40% between the same overall temperature extremes.
It is. And here's a key point. The pump work is tiny. Only a fraction of a percent of the turbine work is needed to run the pump. That's the back work ratio. And it's very low for steam cycles compared to gas cycles. Almost all the turbine work is useful net output.
So why the big efficiency gap compared to Carnot, even in this ideal Rankine cycle? If it's internally reversible, where's the loss?
The gap comes from external irreversibility, specifically how heat is added. In Rankine, you're heating liquid water up to boiling, then boiling it, then superheating steam, all at constant pressure, but not constant temperature. You're adding a lot of heat at temperatures significantly lower than the peak temperature.
Unlike Carnot, where all heat is added at the maximum temperature.
Exactly. That difference, adding heat over a range of temperatures instead of just at the top, accounts for much of that efficiency difference compared to the theoretical Carnot limit.
But that 26% is the ideal Rankine. And here's where it gets really interesting, right? Because the real world throws curveballs. What happens when we build an actual power plant based on this?
Yeah, reality bites. Actual cycles always deviate from the ideal Rankine because of irreversibilities, things that cause losses.
Like what kind of things?
Well, first, fluid friction. As the steam and water flow through pipes, the boiler, the condenser, there's friction. This causes pressure drops.
Meaning the pump has to work harder and the turbine gets less pressure pushing it.
Exactly. It's a double hit. You need more pump work and you get less turbine work. Then there's heat loss.
Just heat leaking out.
Yep. Steam is hot. Surroundings are cooler. Heat inevitably leaks out from pipes and components. To get the same power output, you have to put more heat in the boiler to compensate, which lowers efficiency.
Makes sense. What else?
The big ones are pump and turbine inefficiencies. Real pumps and turbines aren't perfectly isentropic. They have internal friction, turbulence, losses. We measure this with isentropic efficiency, how close they get to the ideal. Maybe 85% for a pump, 87–90% for a large turbine, but never 100%.
Okay, so the main components themselves aren't perfect.
Right. And there are other smaller things too, like subcooling in the condenser, cooling the liquid a bit below saturation temp. This helps prevent cavitation in the pump.
Cavitation sounds bad.
It is. Tiny vapor bubbles forming and collapsing violently. It can literally eat away at the pump impeller. So subcooling helps, but it represents a small energy loss. Plus, bearing friction, steam leaks, air leaking into the low-pressure condenser, power used by fans, other auxiliary gear, it all adds up.
So all these real-world imperfections chip away at that ideal efficiency.
They really do. If that ideal cycle we talked about was maybe, let's say, aiming for 43% in a better scenario, a real plant with typical component efficiencies might only achieve 36%. Those irreversibilities have a significant impact.
Okay, so engineers are constantly battling these losses. Friction, heat leaks, imperfect machines. How do they fight back? What's the core strategy for clawing back some of that lost efficiency?
The fundamental principle is pretty straightforward, actually. You want to either increase the average temperature at which heat is added in the boiler or decrease the average temperature at which heat is rejected in the condenser.
Widen the temperature gap the cycle operates over, basically, but focusing on the average temperatures.
Exactly. The bigger the effective temperature difference the engine works across, the more efficient it can be. It's about maximizing the average high temperature and minimizing the average low temperature.
Okay, so how do they do that in practice? What are the main levers they pull?
Well, one key way is lowering the condenser pressure. If you reduce the pressure in the condenser, the steam will condense at a lower temperature.
Lowering the average temperature of heat rejection.
Precisely. This directly boosts thermal efficiency and the network you get out. That's why power plant condensers operate under a strong vacuum, well below atmospheric pressure.
What's the catch here? Is there a limit or downsides?
Definitely downsides. There's a practical lower limit set by your cooling source. If you're using river water at 15 degrees C, your condenser needs to be warmer than that, say 25 degrees C, to actually transfer heat. That sets a minimum pressure.
Makes sense.
Also, putting a strong vacuum increases the risk of air leaking into the system, which messes things up. But the critical side effect, lowering condenser pressure, significantly increases the moisture content of the steam leaving the turbine.
Back to the wet steam problem, ruining the blades.
Back to the wet steam problem.
Yeah.
It's a major trade-off. More efficiency, but potentially more damage.
Okay, so that's lowering the bottom temperature. What about raising the top temperature?
The second main method is superheating the steam to high temperatures. You heat the steam well above its boiling point at the given pressure. This raises the average temperature where heat is added.
And that boosts efficiency, too.
Yes, increases thermal efficiency and network. And it does this without necessarily raising the boiler pressure, which has its own issues.
Now, what about that moisture problem we just encountered with the lower condenser pressure? Does superheating make it worse or better?
Better. This is a huge side benefit. Superheating significantly decreases the moisture content at the turbine exit. It makes the steam drier.
Oh, that's very desirable. Protects the turbine.
Absolutely. But again, there's a limit. It's called metallurgical considerations. Basically, how hot can the turbine blades get before the metal weakens or fails?
Right. The materials have limits.
Exactly. Currently, that limit is around 620 degrees C, maybe 1150 degrees Fahrenheit. Pushing beyond that requires advanced materials, maybe ceramics, which are still under development for large turbines.
Okay, so lower condenser pressure, higher superheat. What's the third way?
The third big one is increasing the boiler pressure. Higher pressure means boiling happens at a higher temperature. This also raises the average temperature of heat addition.
So higher efficiency again?
Yes, higher thermal efficiency. Modern plants run at very high pressures, over 30 MPa, which is like 4,500 psi. Efficiency is around 40% for fossil fuel plants, maybe 34% for nuclear. Some even go supercritical.
Supercritical, what's that?
Above the critical pressure of water, around 22 MP. At those pressures, there's no distinct boiling phase. Water just gradually transforms from a dense liquid-like state to a less dense gas-like state as you heat it. It's a different regime.
Interesting. Now, does increasing the boiler pressure have a downside, like the moisture problem with lower condenser pressure?
Yes, it does.
Yeah.
If you keep the turbine inlet temperature the same, increasing the boiler pressure actually increases the moisture content at the turbine exit.
There it is again, the trade-offs.
Always trade-offs. This is why just cranking up the pressure isn't enough. You need other solutions, which leads us nicely into the more advanced cycle modifications.
Okay, let's see how these play out together. Can you walk us through an example?
Sure. Let's take our baseline ideal Rankine cycle, maybe getting that 26% efficiency we mentioned. If we lower the condenser pressure significantly, say from 75 kPa down to 10 kPa, a much stronger vacuum.
Efficiency goes up.
Right. Efficiency jumps maybe to 33.4%. That's a big gain. But the moisture at the turbine exit also jumps, maybe from 11% to almost 19%.
Oof, getting into the danger zone for the blades.
Definitely. Now let's add superheating. Keep the high boiler pressure and that low condenser pressure, but superheat the steam way up to 600 degrees C.
Okay, what happens now?
Efficiency climbs further, maybe to 37.3%. And the best part, the moisture content drops way down, maybe to around 8.5%. Much safer for the turbine.
Nice. Solved the moisture problem and got more efficient. What about cranking up the pressure now?
Okay, now let's push the boiler pressure way up, say to 15 MPa, while keeping that 600 degrees C superheat and the low 10 kPa condenser pressure.
Efficiency should go up again.
It does. Jump significantly, maybe to 43.0%. A
Yeah.
very efficient cycle.
But
But the moisture content creeps back up, maybe to 19.6% again.
So chasing higher pressure for efficiency brings back the moisture problem, even with high superheat. It really is a constant battle.
It is, and that's exactly why engineers needed another trick up their sleeve.
Right. So increasing boiler pressure gives great efficiency, but brings back that moisture headache. How do engineers get around that without resorting to dangerously high superheat temperatures that materials can't handle? What's a practical fix?
The practical fix is called reheating. It's a really clever idea. Instead of trying to do all the expansion in one go, you do it in stages.
Stages? How does it work?
Steam first expands in a high-pressure turbine down to some intermediate pressure. Then, crucially, it's piped back to the boiler.
Back to the boiler. Mid-cycle.
Yep. And it gets reheated there, usually at constant pressure, often back up to the original high temperature it started at before the first turbine.
Okay, so it gets a second boost of heat.
Exactly. Then this reheated hot steam goes into a second, low-pressure turbine and expands all the way down to the condenser pressure.
Ah, I see. Like a two-stage expansion with a warm-up in between. What does that achieve?
Two main things. First, it generally improves cycle efficiency, maybe by 4 or 5%, because you're adding more heat at a high average temperature. But the primary reason for reheat, especially with high boiler pressures, is to reduce the moisture content in the final stages of the low-pressure turbine.
So it dries out the steam before that final expansion step where it gets coldest and wettest.
Precisely. It keeps the moisture within acceptable limits to protect the turbine blades, even when you're using very high boiler pressures.
Makes sense. Can you do more than one reheat, like 3 or 4 stages?
You could, theoretically, but the efficiency gain drops off. The first reheat gives you the biggest boost. A second reheat might give you half that gain again. A third, even less, diminishing returns.
Okay.
So more than 2 reheat stages usually isn't economically practical. Double reheat is sometimes used, but mostly just in those very high-pressure, supercritical plants.
Interesting history there, too, you mentioned.
Yeah, reheat was actually tried back in the 1920s, but they had operational issues with the materials and control systems back then, so it's kind of abandoned.
Huh.
But as boiler pressures kept climbing in the late 40s and 50s, causing more moisture problems, they brought it back. Single reheat first, then double reheat for the highest pressure plants. It became essential.
And there's an optimal pressure to do the reheating.
Generally, yes.
Okay.
The best efficiency gain usually happens when the reheat pressure is around 1/4 of the maximum boiler pressure. Gives a good balance.
Okay, so reheat tackles the moisture problem from high pressure. But you mentioned earlier that even in the ideal Rankine cycle, we're adding heat to cold water initially, which isn't ideal for efficiency. Reheat doesn't fix that, right? Is there a way to warm up that water before it hits the main boiler?
Excellent point. Yes, there is. That's the idea behind regeneration. The goal is exactly what you said. Preheat the feed water, the water leaving the pump before it goes into the boiler.
How do they do that? Do they use some of the hot boiler gases? Or
You could imagine complex heat exchangers maybe even inside the turbine, but that gets complicated and can actually cause more moisture issues within the turbine itself. The practical solution is much more elegant.
Okay.
They extract or bleed a small amount of steam from the turbine at various points during its expansion.
Wait, they take steam out of the turbine before it's finished expanding? Doesn't that lose power?
It does mean that extracted steam doesn't produce its full potential work in the turbine. But that hot steam is then used to heat the feed water in a special heat exchanger called a feed water heater or regenerator.
Ah, so you sacrifice a little bit of turbine work from that bled steam to significantly preheat the water going into the boiler.
Exactly. By doing that, you raise the average temperature at which heat is added in the boiler because the water entering is already warmer. This significantly improves the overall cycle efficiency.
Clever. Using the cycle's own energy to bootstrap itself.
It is clever. And regeneration has other big benefits, too. It helps to de-aerate the feed over, remove dissolved gases like oxygen that can cause corrosion in the boiler tubes.
Okay, that's important for maintenance.
Very. And it also helps control the steam flow rate. At the low pressure end of the turbine, the steam volume becomes enormous. Bleeding some off actually makes designing the final turbine stages a bit easier.
Huh. Multiple benefits then. Efficiency, deterioration, flow control.
Absolutely. That's why regeneration in some form has been used in basically all modern steam power plants since the 1920s. It's fundamental.
Are there different kinds of these feed water heaters?
Yes, two main types. Open or direct contact heaters, where the bled steam literally mixes directly with the colder feed water. They ideally leave as a combined stream of saturated liquid at the heater pressure. These usually need an extra pump.
Okay, direct mixing.
Then there are closed feed water heaters. These work like a typical shell and tube heat exchanger. The steam and feed water don't mix. Heat just transfers across tubes.
So indirect heating.
Right. They can operate at different pressures and don't necessarily need that extra pump, but they're generally more complex and expensive. Most large power plants use a carefully designed combination of both open and closed heaters to get the best results.
So putting it all together, regeneration boosts efficiency significantly.
Oh yeah, so let's go back to that high pressure, high temperature cycle that got maybe 43% efficiency. If you had just one open feed water heater regeneration, the efficiency can jump to maybe 46.3%.
Wow, another solid gain just from preheating the water.
Exactly. And when you combine both reheat and regeneration, maybe a cycle, with a couple of feed water heaters and one stage of reheat, you can push efficiencies even higher, perhaps up to 49.2% in an ideal calculation.
Okay, nearly 50% just by cleverly rearranging how heat is added and managed within the steam cycle itself. That's impressive.
It really shows the power of thermodynamic optimization. Engineers constantly tweaking things to wring out more useful energy.
It all sounds incredibly efficient, especially with these combined reheat and regeneration cycles hitting close to 50%. But earlier you mentioned external irreversibility and things like heat transfer losses. Is there a way to look at the true efficiency, accounting for the quality of energy, not just the quantity? Like, where are the real unavoidable losses happening?
That's exactly what second law analysis helps us understand. Even our ideal Rankine cycles, which we assume are internally perfect with no friction or internal losses, still suffer from external irreversibilities.
Like that heat transfer from the very hot furnace gases to the relatively cooler steam in the boiler.
Precisely. That's the biggest one. You have heat flowing across a large temperature difference. From a second law perspective, which considers energy quality or exergy, that represents a significant destruction of work potential.
So exergy is like the useful work potential of energy,
Yeah.
and it gets destroyed by things like inefficient heat transfer.
Got it. Second law analysis pinpoints where this exergy destruction, this loss of potential work, is largest. And guess where it usually happens?
In the boiler, during that heat addition process.
Exactly. In a typical ideal Rankine cycle example, the largest exergy destruction by far occurs during the heat addition in the boiler. Maybe over 600 kilograms of exergy destroyed there, compared to zero, ideally, in the isentropic pump and turbine.
Wow. So even in a perfect internal cycle, the way we get heat into it is inherently inefficient from an energy quality standpoint.
That's a key insight from the second law. It tells us that even if we perfect the pumps and turbines, improving how we transfer heat into the cycle offers huge potential for improvement. The second law efficiency of the cycle, which compares actual work to the maximum possible work considering the heat source and sink temperatures, might only be around 41–42%, even for an internally ideal Rankine cycle.
Okay, that puts things in perspective. Now, thinking about losses. Traditional power plants reject a massive amount of heat in the condenser, right? Just dumped into rivers or the atmosphere. Feels like such waste.
It is, from one perspective. That condenser heat is low temperature, low quality energy, difficult to turn into more electricity efficiently.
But what if that heat isn't really waste? What if some industries could actually use that kind of low to moderate temperature heat?
You're thinking exactly along the right lines.
Yeah.
Many industries, chemicals, paper mills, food processing, textiles, need large amounts of process heat, often in the form of steam at, say, 150 degrees C to 200 degrees C. Now, think about it from that second law perspective again. Does it make sense to burn fuel in a furnace at maybe 1400 degrees C just to generate steam at 150 degrees C?
No, that sounds like using a sledgehammer to crack a nut. A huge temperature drop, lots of exergy destruction.
Exactly. It's highly inefficient in terms of energy quality. You're using high-grade heat for a low-grade task.
So is there a way to bridge that gap? Use the power generation process to also supply that industrial heat more efficiently?
Yes, and that's called cogeneration, sometimes called CHP, combined heat and power. It's the simultaneous production of more than one useful form of energy from the same fuel source, typically electricity and process heat.
Okay, two products for the price of one fuel input.
Pretty much. And it makes perfect sense because industries need and process heat almost always need electricity too. Why generate them separately and inefficiently?
Right. So how does a cogeneration plant work, ideally?
In the most ideal cogeneration setup, you design the plant so that all the steam leaving the turbine is at the right temperature and pressure needed for the industrial process. There would be no condenser at all.
No condenser, so no waste heat rejected to the environment.
Ideally, yes. All the energy that isn't converted to electricity in the turbine goes out as useful process heat. In this scenario, the utilization factor, which is net power plus process heat, divided by total heat input, could be 100%.
Wow, 100% utilization. That's amazing compared to a 40% efficient power-only plant.
It is. Of course, real plants aren't quite 100%, but they can achieve utilization factors of 80% or even higher, which is still a massive improvement in overall energy efficiency.
How do practical plants handle things? What if the need for heat and powers doesn't match perfectly?
Good question. Practical plants need adjustable loads. They're usually designed so some steam can be extracted from the turbine at the right pressure for process heating, while the rest continues expanding through the turbine and goes to a condenser.
Ah, so they still have a condenser, but it handles less steam.
Exactly. This allows them to vary the ratio of heat to power production. They might also have a valve to send high-pressure steam directly from the boiler to the process heater, bypassing the turbine entirely if maximum heat is needed. Or, if there's no process heat demand, they can run just like a regular power plant, sending all steam through the turbine to the condenser.
So they're flexible.
Very flexible. Cogeneration isn't actually a new idea. It was used for district heating, supplying heat to buildings in cities early last century.
Really?
Yeah, but it kind of faded when fuel got really cheap. Then, the energy crises of the 1970s brought it roaring back because the fuel savings are so significant.
And now?
Now, they're seen as economically very attractive, and lots of new cogeneration facilities are being built, especially integrated with industrial sites.
Can you give an example of how the numbers might work out?
Sure. Imagine a plant designed for both. If it runs purely for maximum process heat, throttling all steam, it might supply, say, 41,000 kilowatts of heat with nearly 100% utilization but zero power. If it runs purely for power, no process heat, it might produce 20 milliW of electricity at maybe 40% efficiency, which is the utilization factor in this case.
Right.
But in a typical cogeneration mode, maybe extracting 70% of the steam for process heat and sending the rest through the full turbine, it could supply, say, 26 milliW of process heat and still generate several megawatts of power, achieving an overall utilization factor of 86.5%.
That's a huge jump in overall energy use efficiency. It really makes sense where you need both heat and power.
Definitely. It's a much smarter way to use fuel resources.
Okay, we've seen how engineers squeeze amazing efficiency out of steam cycles alone with reheat, regeneration, and using waste heat in cogeneration. But the push for even higher efficiency never stops. What's the next level beyond optimizing just the steam cycle?
The next big leap is the combined gas-vapor cycle. Usually this means putting a gas turbine Brayton cycle on top of a steam turbine Rankine cycle.
Okay, combining two different types of cycles, how does that work?
It leverages the fact that gas turbines operate at much, much higher temperatures than steam cycles. We're talking turbine inlet temperatures well over 1400 degrees C, sometimes approaching 1500 degrees C. Remember, steam cycles are stuck around 620 degrees C because of material limits.
Right, gas turbines run way hotter.
So the gas turbine runs its cycle, compresses air, burns fuel, expands hot gas through its turbine to generate power. But the exhaust gas coming out of that gas turbine is still incredibly hot. Maybe 500 degrees C or 600 degrees C.
Still hot enough to boil water easily.
Exactly. Instead of just venting that hot exhaust to the atmosphere, which wastes all that high-temperature energy, a combined cycle uses it as the heat source for the steam cycle's boiler.
Ah, so the gas turbine's waste heat becomes the steam turbine's input heat. It's like cogeneration, but between two different power cycles.
Precisely. The steam cycle acts as the bottoming cycle, recovering heat from the topping gas turbine cycle. It's a perfect marriage because their temperature ranges complement each other so well.
And this significantly boosts overall efficiency.
Dramatically. You get the power output from the gas turbine, plus the power output from the steam turbine, all from the same initial fuel burned in the gas turbine. The overall thermal efficiency is much higher than either cycle could achieve on its own.
Without a huge extra cost compared to building two separate plants?
Generally, yes. The cost is higher than a simple cycle plant, but the efficiency gains are so large that it's often the most economical choice for new, large-scale power generation. That's why most new efficient power plants are combined cycles, and many older steam plants are being repowered by adding a gas turbine on top.
What kind of efficiencies are we talking about?
We've seen incredible progress. Back in the 80s, they were hitting maybe 44%, then 52.5% by the late 80s. But recently, a plant in Germany hit 60.8% in 2011. GE claimed 62.2% in France in 2016.
Over 60%. That's a massive jump from the 40-something% we were talking about for even advanced steam cycles.
It really is. And the target now is pushing towards 65%. We're getting remarkably close to the theoretical limits for the temperatures involved. It's a huge success story for thermodynamics in action.
Can you give a quick example of the combined effect?
Sure. If you had a gas turbine cycle that on its own was maybe 27% efficient, and a steam cycle that on its own, using a conventional boiler, was maybe 41% efficient. When you combine them properly, using the gas turbine exhaust to power the steam cycle, the overall combined plant efficiency could jump to nearly 49% or even higher in optimized designs.
Wow. Clearly shows why combined cycles are the state-of-the-art for efficiency right now.
Absolutely. They dominate new installations for fossil fuel power generation.
Okay, combined cycles are amazing, hitting over 60% efficiency. But you know engineers, they never stop asking, what if? What if water isn't even the best fluid to use, even in that steam bottoming cycle? Could something else push efficiency even higher?
That's a great question, and it leads to the concept of binary vapor cycles, although they're less common commercially than combined cycles right now. The truth is, water, while convenient, is far from being the ideal working fluid thermodynamically.
Really? What would an ideal fluid look like?
Ideally, you'd want a fluid with a very high critical temperature, much higher than water's 374 degrees C, so you could add heat at the highest possible temperatures allowed by materials. You'd want its saturation pressure at those high temperatures to be reasonably low, not astronomically high like water's.
Okay, high critical temp, manageable pressure.
You'd also want a low triple point temperature, so it doesn't freeze in the condenser. And you wouldn't want the condenser pressure to be too low to avoid those air leak problems we talked about. High enthalpy of vaporization is good, absorbs lots of heat, and ideally an inverted U-shaped saturation curve on a TS diagram.
Why that shape?
That shape means that even isentropic expansion tends to end in the superheated region, or at least very high quality. It naturally avoids the wet steam problem in the turbine. Water has more of a V-shape, leading to moisture issues. Plus, good heat transfer properties, non-toxic, non-corrosive, cheap, available. List goes on.
Water definitely fails on some of those.
Yeah.
The critical temperature is low compared to material limits, pressures get very high, and it has that moisture issue.
Exactly. So the idea of a binary vapor cycle is to use two different fluids in two separate Rankine cycles, one stacked on top of the other.
Kind of like the combined cycle, but with two vapor cycles instead of gas and vapor.
Precisely. You choose a fluid that's good for the high-temperature topping cycle, and another fluid, often water, that's good for the low-temperature bottoming cycle. The key is that the condenser of the topping cycle acts as the boiler for the bottoming cycle.
Heat rejected by the top cycle boils the fluid in the bottom cycle. Clever. What fluid works well for the top cycle?
Mercury was a leading candidate. Its critical temperature is almost 900 degrees C, well above material limits, and its critical pressure is only about 18 MPa, quite manageable. So mercury is great at high temperatures.
Okay, so why not just use mercury for the whole cycle then if it's so good at high temps?
Because mercury is terrible at the low temperature end. At typical condenser temperatures, its saturation pressure is incredibly low, almost a perfect vacuum. Air leakage would be a nightmare. Plus, mercury is highly toxic and very expensive.
Right, big practical problem. So mercury on top, water on the bottom.
That was a classic binary cycle studied. Mercury handles the high temps efficiently, rejects heat at a temperature suitable for boiling water, and then the water cycle handles the lower temperatures down to the final condenser. This combination allows the overall cycle to operate over a wider temperature range and approximate the ideal Carnot cycle more closely.
And the efficiency potential.
Studies suggested efficiencies of 50% or even higher were possible. In fact, a small 40 million W mercury steam plant was actually built and operated in New Hampshire back in the 1950s. And it reportedly had a higher efficiency than most large conventional steam plants of that era.
Wow. So why aren't binary cycles common now if they were so efficient?
Mostly economics and practicality. They have a very high initial cost. You need two separate fluid loops, specialized components, and have to handle fluids like potentially toxic mercury. And meanwhile, the combined gas steam cycles we just discussed have become so successful and efficient, reaching over 60%, that they offer stiff competition at a potentially lower cost and complexity.
So Technically brilliant, but economically overtaken by combined cycles for now?
That seems to be the case. The efficiency potential is there, but the cost and complexity haven't made them attractive compared to the alternatives,
Yeah.
especially the highly optimized combined cycles.
Okay, so wrapping this up, what does it all mean? We've journeyed from the pure theory of Carnot through the practical workhorse Rankine cycle and seen just layers upon layers of engineering ingenuity, reheat, regeneration, cogeneration, all designed to squeeze more useful energy from the fuel.
Yeah, and then the leap to combining gas and steam cycles, pushing efficiencies past that remarkable 60% barrier. It really is a story of relentless optimization.
It's this continuous pursuit, getting more energy out of the same input, driven by physics, material science, economics, just sheer cleverness. Every fraction of a percent gain saves fuel, reduces emissions, lowers costs.
Absolutely. These aren't just abstract numbers, they have real-world impact.
So as you, our listeners, think about how our world is powered, the lights, the computers, everything, maybe consider this. What innovations might be next? We've seen cycles combine, waste heat recovered. What other seemingly wasted energy sources or clever thermodynamic tricks might engineers harness in this ongoing quest for ever higher efficiency?
It's a field that never stands still. The fundamental drive to do more with less is always pushing the boundaries.
Definitely something to think about. Thanks for that deep dive today.
My pleasure. It's a fascinating topic.